Hello. I hope everyone can hear me. I am. I will start my introduction. I think people are still joining. Um,
Okay.
I am Chandravardhan. I am from India. Uh, right now, I am working for a PSU as a senior project executive. So I used to teach the students as a subject expert for the civil engineering subjects for graduate students as well as postgraduate students. And my hobbies, I like teaching through the digital platforms, and yeah, I started taking the FE classes through the team Bhavanam C2C, and I think few of you are already taking the courses, right?
Yes.
Okay.
Yes.
Okay. So some of you might be working, some of you might be studying, having your what we say masters. Is it so?
Yes, sir.
Acha. So how many of you are giving FE exam in September?
I am giving this last week, August last week.
Okay, nice, good. Okay, then I'm starting the actual session. I'm sharing my screen here. I hope everyone is able to see the screen.
Yeah, we can hear you.
Yes.
Yeah.
Yes.
So I'm going to take the subject mechanics of materials, and for the FE exam conducted by NCEES, this has a weightage of around 7 to 11 marks. For safe side, we can say that we can get around 9 questions on an average, which we'll get in our hands while the exam. So basically, strength of materials, what we studied in BTech is very lengthy. Knowledge is very vast. But luckily for the FE exam, the syllabus is very minimal, and also the FE provides handbook. Reference handbook is provided by FE, and it has all the formulas. So our advantage here is you need not to remember any formula. It is as easy as you think. It's like an open book exam. But thing is that you have to be very careful with the units, and you have to be very careful with the sign conventions, and you have to be careful with applications. So you need not to worry about the memory, you need not to worry about the logic. This exam won't be as tough as, in India, people think that IIT, GATE or the tough exams. It's like 10% of GATE level. You just need to find the formula from the reference book and then apply it, use the calculator, get the answer, and choose the correct option. That's the only thing. And for example, I will show you here an FE handbook. uh, this is the extraction of FE handbook. I just collected the pages which are related to mechanics of materials only. There are just 13 pages, and here they have mentioned the some syllabus like stress strain curve, different types of strains, different types of stresses, and more circle. All the things are already mentioned in this handbook. You just need to be thorough with the handbook well in advance, so that it will be faster for you to reach the formula in the handbook. And coming to the syllabus here, there are just plain stresses and strains, and combined stresses, principal stresses, and more circle. The very famous shear and bending moment diagrams, as well as the deformations. And coming to the importance of this subject is the basics for all the structures related subjects. So I request all of you to be very attentive to this session. I will teach you all the basics For the first session, this is the first session for you. This will be a bit lengthy, but it will be very elaborate. It may be time taking, but it will be elaborate so that it will be easier for you for the further sessions. So as I said, my profile is here. My name is Chandravardhan. I am working as a senior project executive for a major project in India. I did my MTech from IIT Madras and BTech from NIT Calicut. So I made this, I made these notes particularly meant for FE exam. After this completion of all the sessions by me, you can directly refer only these notes and you will get 8 to 9 marks for sure. So you can save this PDF, you can save this in mobile, and whenever you have time while you are on transit, you can revise it, recall it, and practice it. So now I'm starting with important units and conversions. As I said, you need not to worry about the formulas. You just need to attentive on units. So that's why I'm starting this session with the units. In India, while in BTech, some of you might have studied in international standards where meter, Newton, kgs, like this you might have seen. But for the FE exam, they can ask both the units. They can ask SI units as well as USCS units. That's why you must be aware, and also you need not to worry. FE book has also mentioned as a given a table where you can use the factors to get the conversions of units. So if I consider the length, first you have to know about the prefixes. Prefixes, you might have already seen that millimeter, milli means 10 power minus 3. Micro means 10 power minus 6. For example, if I take 1 millimeter, it means that milli means 10 power minus 3. That is 10 power minus 3 meter. 1 millimeter is equals to 10 power minus 3 meter. And if you take this to the other side of the sign, then it becomes 1 meter is equals to 1000 millimeter. This is as simple as that. It's a like plus 11, 12th syllabus. Centi means 10 power minus 2. 1 kg. Kilo means 10 power 3. And centifoot means 10 power minus 2. So out of all these prefixes, what we generally come across in mechanics of materials are mega 10 power 6. You might have seen megapascal means 10 power 6 pascals. Giga means 10 power 9. Nano means 10 power minus 9. So just remember them. You can get them in handbook also. And there are in India we use like kilometer. It is some town is around 100 kilometers from Hyderabad. But the thing in US, you might have already seen that they use the term miles, and 1 mile is equivalent to 1.61 kilometer, and 1 meter is equals to 3.28 feet. These are the different US versus SI unit conversions. These are the basic things. By this, we can complete MOM FE exam. Here, I'm giving a simple example for unit conversion. Suppose speed of a vehicle is 40 kilometer per hour. What is the speed in USCS system? That means miles per hour. How to calculate it? Using the handbook. Here I have attached the handbook also, a screenshot, and given the reference there. So how to use it means the speed of the vehicle is 40 kilometer per hour. If the unit is in kilometer per hour, the handbook says multiply that quantity by this factor. This factor is 0.621. So I multiply 40 into 0.621. This is a factor I get from FE book. Then I will get the answer in miles per hour. This is as simple as that. Is my speed fine for you, or shall I faster it or slow it down?
I think it's fine, sir. Thank you.
Thank you. And these are the units for length I have said. And coming to the mass, mass, it is a very what we say in India, we use kgs. In US, we use pounds, and generally we measure it by pound mass, and pound is generally represented by the symbol LB. LB means it's a Latin word, libra, and the shortcut is LB. So don't confuse with that. Pound is nothing. Its a symbol is represented by LB, and 1 pound mass is equal to 0.45 kgs, or the revision is 1 kg is equals to 2.2 pound mass. And these are the other two types. These are not much used in FE exam, but you can have a look for this. And there are some important points to be noted. The weight and mass. Mass is not linked with gravity, but the weight is linked with gravity. Mass, they will measure by pound mass, and the weight they will measure by pound force, because it is due to gravitational force. But I will give you clarity further in the coming pages. And coming to the force, in India you might have seen newtons. In US they will call it as pound force or kg force. Pound force, or the newtons, it is equivalent to kg meter per second square. I will give you an example for this also. So LB force, I already said, LB force is not equal to LB mass. It is a unit for mass. LB force is unit for weight. Always remember this. Again, I'm going to start with an example. I will give you the clarity here. How to convert a unit for force into UCSS pound force, like that. Suppose I'm taking an example here. A force of 10 kilonewton is applied on a plate of surface area 10 square meter. What is the pressure in the PSI? PSI means pounds per square inch. So in the notes I have shown you here, PSI, that is for stress or the pressure. These units are Newton per meter square in SI system, or pound force per inch square, which we shortcut for as a shortcut we mentioned by PSI, pounds per square inch. Let's see how we convert that. So this is an example. For a demonstration I'll show you. Here 10 kilonewton of load is acting on a plate. Suppose the weighing machine is a plate. It has 10 square meter area. So what is a stress or pressure acting? And what is stress versus pressure? That is also you will come into the actual subject. I will teach you there. Suppose pressure is equals to force by area. This is a basic formula. And force I have given here. Force is 10 kilonewton. I wrote it here. And area is 10 square meter. Now 1 kilo, as I said, the prefix is 10 power 3. So 10 into 10 power 3 into Newton by 10 centimeter square means centimeter into centimeter. Now I want to convert it into USCS system. So that means I have to convert newtons as well as centimeter. So what is 1 Newton equal to dash pound force? For that, again, come to in the exam. While in the exam, you will be free to use the handbook. Open the handbook, search for the first few pages. You will get this page. This is a screenshot of that page. Here, all the units are measured in what we say alphabetical order. First, all the things coming with C, E, F, G, all in alphabetical order. So you keep on searching like this. You come to know that there is the word Newton. And for the Newton, it is given the factor is 0.225. So what we have to do? We have to multiply this quantity by 0.225 to get pound force. And similarly for the centimeter, 1 centimeter is equals to how much inch? Here again come to that page of the handbook and keep searching in chronological order. You will come to know there is centimeter here. 1 centimeter is equals to 0.394. So 1 centimeter is 0.394 and there are centimeter squares. So they will get 2 centimeters, and that's why we get two factors here. Don't forget this. People will blindly here. This is where the FA exam will check your basics. 10 centimeter while converting it to inch. Don't do it like 10 into 3.394 inch square. There we make the mistake. It is 10 into 0.394 into 0.394, then inch square. That's why I have split the equation here for easy understanding and not to avoid the error. Not to. So now we got this from formula or whatever data. Now the data is ready. In the FE exam, again you got the freedom to use the calculators. And what type of calculators to be used? Some of you might have seen in the previous classes, but I will show you again. Some of the people might have joined today. So the FE website officially has mentioned some calculators that can be used. Here are the Casio related calculators. Whatever the series have these letters 115 or 991, they can use these calculators if they are of Casio company. If they are of HP company, again they have mentioned from series, you can use from them. I After this session, I will share you the link of this page. You can go through them. So using the calculator, you will feed all this data, and you will get the answer as 144.9 pounds per inch square, and its shortcut is PSI. That's it. Is it clear?
Yes.
Yes.
Yeah. Okay.
So
Any doubts till now?
nothing for now.
Okay. So as I said, the most confusing thing in USCS system is pound force versus pound mass. It's not that much confusing. I just uh, uh, letting you know that you have to be very careful. That's it. So pound mass is simply the mass, and it's a constant independent of the gravitational field. Whether you are on Earth or you are on Moon, your mass will be 60 kgs only. And pound force is nothing but the weight of that mass for a particular gravitational field, and the formula is m mass into g, where we can see the effect of gravitational effect. That's why weight of a person on the moon is generally, we studied in our 10th physics that 1/6 of the weight on the earth. Why weight changed? Because gravitational force has changed on the moon. Now if I want to get the force in pound force, suppose I got a quantity in pound mass, I want it to be in pound force, we need to add a constant called GC, gravitational constant. Why we must add it is, in physics, you just need to remember this point that in physics we have to maintain dimensional homogeneity. If on the left hand side dimensions are kgs, the right hand side should be also dimensions kgs. If left hand side it is kg into meter, here also it should be kg into meter. To maintain that, we have to use the constant like this here. Just remember this value. I will show you an example for this gravitational factor gc. Here the example, yeah, my question is here, 1 pound force is equivalent to how much amount of newtons, which is an SI unit, how much it is they are asking. So what I do here is I will consider 1 Newton. 1 Newton is equals to this. Why? Because force is equals to mass into acceleration. 1 Newton is equals to mass is kg, acceleration is meter per second square. That's why I got 1 Newton is equals to 1 kg meter per second square. Okay. And again, by using this handbook, I got that 1 kg is equals to 2.2 pound mass. Remember this? And 1 meter is equals to 3.28 feet. Remember this point, feet. And in bottom, second square will remain as it is. But to maintain the, as I said, dimensional homogeneity, something, etc., etc., just remember this point divided by 32.2. And the units are pound mass, feet by pound feet, second square. After that, you can see that the units gets cancelled. Pound mass by pound mass, feet by feet, second square by second square. So After doing this, we got this data with the units lb force, pound force, which is equivalent to 0.226. 1 newton is equal to 0.226 pound force. This is a fact. You need not to worry about this again. This is already available in our handbook. Just go back here and you can see that somewhere in the previous example I have shown you here. I have said that 0.226 we got in that example. To be accurate, it will get 0.225. So this is about the units. The thing about unit is over. Just refer the first few pages. You will not be having any worries. Coming to the actual topic, stresses. You know, mechanics. I said mechanics of materials is a basic subject for all the structural related subjects. And in every subject, you will come across the word stress. In your real life also, you will always face some work stress. You know, relationship stress. I will give some examples. Stress in our science and stress in our life can be correlated. I will show you. It's a very wonderful comparison. You know, stress is internal resisting force offered by the material against the deformation or external applied load per unit area of the plane. As simple as that. Suppose I have mentioned here a member and I applied a load and I pulled it. It is fixed to one end. I pulled it with some load 10 kilonewtons. Then this material is a group of atoms. All these atoms are connected to each other by intermolecular forces. Now what you did, you come from outside, you applied some external load and try to elongate it. You means that you're trying to elongate, you are trying to break the bond between the atoms. So it's a tendency of the nature, it will resist it. Why you are opposing my design? It's a nature's design, God's design. So it will start resisting. Because of that resistance, there will be internal resisting forces. There is no much rocket science in this. It's just internal resisting forces, which is uh, by the area of the cross section is simply the stress. Okay, now coming to the types of stresses. Primarily, there are many types, multiple types, but to be fact, there are only two types. That is, first type is normal stress, and the second type is we'll get across it. It is a shear stress. So, what is normal stress? Normal stress is also a stress. So obviously it is an internal resisting force. This is as a nature of act of nature. It is acting in normal direction. Word here normal in the science terms is perpendicular direction. So in the perpendicular direction to the plane or cross section of a member subjected to external load. Suppose if this is my member, it is tied here and there is no external load, no external factor disturbing it. There will not be stress. Stress is equal to zero. The stress will act only if we try to disturb its uh, intermolecular forces. If I applied external load, then only stresses will act. Now I will show you some pictorial explanation. It's very simple. Suppose I have considered a cylindrical rod here and applied a load on either side, try to pull it. Then what happens? Let's see. Then what happens inside? Let's cut a cross section. As I shown here, I have cut a cross section here. Now, if I deep see this, there will be internal resisting forces against the applied load. If I see that this half of the body will get resisting forces against this direction. If I see this half of the body, will get the resisting forces in the opposite direction. It means that the resistance will be the opposite direction. And further, if you zoom it and check it, what's going on here internally, yeah, these internal resisting forces will be equal to external forces P. Why it should be equal is, again, there is some nature science law. Nature follows again always some laws. It's like equilibrium law. If a body is at rest, resultant of all the forces acting on the body should be zero. To satisfy this law, these internal forces developed. Suppose it is P, it is P1, P2, P3. Some of this, all these internal forces will be equal to the external load P. You remember that point? Now, as per definition, the normal stress is equal to internal resisting force acting normal to the plane, perpendicular to the plane by area. And since equilibrium has to be maintained, this internal resisting force should be equal to F by A. That is that's a derivation of the formula, the meaning of the actual formula for stress. And units for force in SI units, it is Newton, by area is meter square, and UCSI units, it's a pound. Generally, people in US, they will use pound for both mass and weight interlinked. Somewhere they for weight also they will use pound, for mass also they will use pound. But while in FE exam, be careful, for mass use LBM, for force use LBF. And that's the only units thing. To avoid, just remember this point: stress is equal to internal resisting force by area of cross section. That's it. The entire explanation is for your understanding. They won't be asked in an exam, so don't just confuse your brains. And coming to types of normal stress, as I said, there are many types of stresses. If you go into stress, there will be normal and shear stress. Again, if you go deep, normal will be of two types, shear will be of two types. So coming to the normal stress, as I said, the stresses that acts normal or perpendicular to the plane. Again, it is of by minimum common sense, we can say that anything that pulls the body is a tensile stress. Anything that compresses the body is compressive stress. But for our exam, remember this sign convention: the tensile stress has to be denoted by positive, and the compressive stress to be denoted by negative. That's the only thing you have to remember. And I have explained the formula here. This is I made this note so that my presence is not needed. You can happily go through as it as a novel. You can get through the concepts easily. Again, I have mentioned the formula here: internal resisting force by the area. And here you will get a new concept called area. Okay. So coming to the stresses, I have simply said that it is internal resisting force by area. But coming to the area, it again there are many types. Suppose I take a member here and fix it here and applied a load P. Are you here? Are you able to hear me now?
Yes, sir.
Yes.
Okay. So after applying this load P, this member will obviously elongate. Suppose this is not a rigid, there are different types of materials: rigid material, elastic material. So if it is an elastic material, it will elongate. After elongating, if initial area is A1, its final area is A2. A2 will obviously be less than A1. Why? Because the mass can neither be created nor be destroyed. It's a God's design. God has uh, generated some mass on Earth, so it cannot be destroyed. It can be break into pieces. That's why A2 will be less than A1. As we keep on applying this load, at every instant, this area keeps on decreasing. Suppose at instant t1, at t0, at the initial time, if they ask me stress, the stress is equals to applied internal resisting force by initial area A1. At the time t1, after some 10 minutes, the stress will be equal to internal resisting force by the area at that instant t1, which will be A2, that is reduced. Again, at the time t2, if they ask me what is the stress this member has been undergoing because of external load, then it will be internal resisting force by A3. So we can generalize here that with time the area decreases. So here comes the new concept called what is true stress or actual stress or instantaneous stress. These are the different names we call this for this type of stress. If they ask me, um, please, if they ask you find the stress at the instant of 1 hour after applying load, though you have to use the area at that instant. You just remember in the question they will give that A member is subjected to load of 10 kilonewton. Its initial area was 10 square meter. After 1 hour, the area was reduced because of the load it has been undergoing. Then you have to use that 5 square centimeter if that area is at that time. That's the only difference. Just remember that this is called true stress, actual stress, or instantaneous stress. And the stress which we have mentioned here without any prefix name, it is just engineering stress. For engineering purposes, we always use the initial area without worrying about what it has been undergoing later. And as I said that units of stress, generally the normal stress is denoted by sigma, by the symbol sigma, force by area. To be frank, to be very precise, internal resisting force by area, Newton per meter square, pounds per inch square. Shortcut is PSI. And one more thing to remember in SI units is 1 Newton per meter square is equivalent to 1 Pascal, and 1 MPa is also a Newton. It's also a unit for pressure or stress. And as I said, that prefix mega is 10 power 6, and Pascal is Newton per meter square, so it is 10 power 6 Newton per meter square. So like this, so again, if you convert this meter into mm square, it will become 1 Newton per mm square. So you just remember this point, 1 megapascal is nothing but 1 Newton per mm square. This is all about the units of the stress. Let's clear our doubts, clear our clarify our understanding here through an example. A steel bar with a cross sectional area. Cross sectional area means cross means in this direction. With a cross sectional area of 5 square centimeter is subjected to axial tensile load of 50 kilonewtons. So its axis is this. They said axial, that means the load will be through these directions, and they said tensile, that means it will elongate it of 50 kilonewtons applied at each end of the bar. What is most nearly the stress in the bar in the units, SI units as well as pascals in terms of MPa, in terms of UCSI units pounds per square inch. Let's see through this. And here I have to mention you that in FE exam they won't ask you the exact digits, like answer won't be in 0.1126, 0.11493. This won't be this much accurate. You can just roughly estimate the answer. You can give that nearly the answer using the options. Coming to the conventional way of getting the answer, the tensile normal stress is force by area, and the force I have said external load is 50 by area is 5 square centimeter. And see the sign notation here. I said I used plus here because tensile stresses should be mentioned through plus sign. And 1 kilo is 10 power 3. I have noted it here. And 1 centimeter square is equal to, here you have to be very careful, 1 centimeter square is equal to 1 centimeter is equal to 10 power minus 2 meter whole square. So it is gonna become 10 power minus 2 whole square into meter square. Just be thorough with this step. After that, simple calculations using the calci, you will get 10 power 8 Newton per meter square. So one of the answer is over. The answer is 10 power 8 Newton per meter square. The stress is. And they asked me to find it in pascals. As I expressed, shown you before, 1 Newton per meter square is equal to 1 Pascal. So use the factor 1, then it will be 10 power 8 Pascal. 10 power 8 Newton per meter square is equals to 10 power 8. And then this is also over. They asked me stress in the units MPa. You know, as I said, MP means mega. It's a prefix. Mega means 10 power 6. It will be 10 power 6 pascals. Let's see how to get that. So I said that 1 megapascal, you can get the answer from this also. Just 10 power 8, 1 megapascal means 10 power 6. If you divide it by this, then you will get 1 megapascal. I will show you how to get answer from here. 1 megapascal is equals to 10 power 6 pascals. Then 1 pascal is equals to 1 by 10 power 6 megapascal. Use this factor here, as simple as that. 10 power 8 into the factor is 1 by 10 power 6 megapascals. The answer is 10 power 2. As simple as that. 10 power 2 means 100. So we got the answer 100 megapascals. Clear? Is it clear? At least can you hear me?
Yes.
Yeah, yeah,
Yes.
yeah. So my third question is also solved in megapascal. The fourth important thing, this is USCS system, United States the system it is. So to get this, first we use this 10 power 8 Newton per meter square which we got in SI system. After that, use the FE handbook. Use this factor. In the previous example I have shown you 0.225 into LBF by 3.281 meter square. This is conversion for meters to inch. Don't forget this square. This is meter square, so factor also gets squared. Always remember, if the unit is squared, factor also should be squared. That mistake should be avoided by this session. And again, this is our unit for feet to inch. 1 feet is goes to 12 inch. Again, there are feet square, so the factor is also squared. Finally, we get the answer in LBF by inch square, whose shortcut is pounds per square inch. That's the way we get the answer. Okay, is it fine? Now it's a test for you. I will
Yes.
randomly. I will just do you people have calculators with you? Are you holding calculator now?
Yes.
Yes. So I will just give a small assignment for you. Just now you have to solve it. Suppose the load is, I say, 25 kilo Newton and area is, I say, 5 square centimeter. What is the normal stress acting? Suppose it is a tensile load. What is a normal stress acting? Can you give me quick answer? Let's see who will give me first. There are around 20 people here. It's very simple. I'm opening the example here. Just go through it. The answer, I need the answer in pounds per square inch. I'm selecting one person. I would like to call Jesu Das. Are you available? Are you available, Jesu Das? Let's solve together. You need to be tensed. Let's solve
Yeah,
together.
I'm here. Yeah, hi.
Okay, okay. Let's solve this then. So it's just go through the simple steps. I'll show you step by step. Normal stress. First, use the formula from the handbook. It is internal resisting force, or simply the force by area. This is correct. Are you clear
Yeah,
with this?
yeah,
Yeah. Now the next step is insert whatever data you have in the question. The load is, I have shown here, the load is 25 kilonewtons. So force is force, yeah, load, whatever, we don't get confused. 25 kilonewton by area is 5 square centimeter. This is clear.
yeah,
Then 25 into This is the prefix kilo, which is 10 power 3 newtons. Clear. Next, 5. To avoid this term, I use that centimeter square. 25 into 10 power 3 newtons by 5 into 1 centi is 10 power minus 2 whole square into meter square. Is it correct?
Yeah.
Yeah.
Yeah. Then use the calculator. Just feed the data as simple as that. 25 into 10 power 3 by 5 into 10 power minus 4. You have to be, these are some basic maths things in our earlier day school days. 10 power minus 2 whole power 2 will be equal to 10 power minus 2 into 2, that is 10 power minus 4. Just remember that. So in my calculator, I am feeding 25 into 10 power 3 by 5 into 10 power minus 4. So I got the answer. How much it is? 5 into some many number of zeros. 1, 2, 3, 4, 5, 6, 7. 5 into 10 power 7 Newton per meter square. You guys got the same answer?
Yes.
Yeah. Okay. Now the answer is not over here. I want my answer in pounds per square inch, that is USCS unit. Let's do this. 5 into 10 power 7, 1 Newton is equal to, as I given in the, let's go to handbook there, and I will open my handbook while in the exam. Imagine this is an exam. After going handbook, I will chronologically check this. I will come to the Newton, and Newton is equals to 0.225 lb. So I'm writing 0.225 lb force, pound force, by square inch. So 1 meter is equals to, I said, how much it is? 1 meter is, where is that example?
3.281.
Yeah, 3.281. 3.281 whole square. The factor has to be squared. Don't forget this. Into, now I got the feet square.
12
Yes,
square.
please. Into 12 square will give me the inch square. So just feed the data in calci again. While feeding the data in calci using these calculators, you will get an option where you can see that denominator by numerator, there will be option. I will show you the screenshot. Where is camera? I guess you guys are able to see the calculator, but there is some shadow over here. See, you will get this option here. This is the calculator is series 991. This is valid for the FE exam. And here, soon after you turn on the calculator, there is one option here, this thing. You just press this, it will make your calculations easy. So feeding this, we get 5 into 10 power 7. So what is the answer? Someone give me. I will just reduce.
258 psi.
How much it is?
7258 psi.
Achha, 7258 psi. That's very good. Your good name, please?
Priya.
Priya. Nice. Nice, Priya. Good work. So this is the way how to do the conversions. And I have shown you the example through the normal stress. And normal stress is just, you can forget everything. Just remember one word. Normal means perpendicular. That's the only thing you have to remember. The stress that acts in perpendicular direction. That is normal stress. Next, we have only 10 minutes left. I will clear you about the shear stress. It is very simple again. Shear stress is also obviously a stress. So stress means the internal resisting force against the intermolecular attractions. But the only change here is this will be acting in parallel or tangential direction. You need not worry about this word tangential also, but just remember at least the word parallel. If my member is like this and another member is like this and applying force here and applying force here, these two members will try to move in the opposite directions. Then there will be a force generated on this plane, and this force is obviously parallel to this plane. That's why this stress will be called as shear stress. So just two words: normal means perpendicular, shear stress means parallel. Entire concept of stresses is completed with this these 2 points. But I will show you the pictorial representation here. I consider the same member, but instead of applying load along the axis, I applied the load in the transverse direction. Transverse means perpendicular direction load, and I consider the cross section here. If you see this internally, the resisting forces are obviously, since they are resisting, they will be in opposite direction to this external applied load. And here I am going to a deep thing. Just you not to, I will clear you one confusion. If the load applied is normal load, which is perpendicular to the cross section, the stress developed is normal stress. But this material is made of infinite number of planes, like a plane like this, a plane like this, a plane like this. If I cut my section through this plane, here there will be normal stress also, as well as shear stress. To resist this normal directional external load at some inclined section, there will be both normal stress as well as shear stress to maintain this equilibrium. Just remember that. Don't simply think that since the load is in this direction, if they ask the shear in this direction, don't say it's zero, because there is no load in this direction or in this direction. There can be the shear stress. Uh, for much more clarity, we have to go into its roots, but we don't need that much level in FE exam. Just remember this fact. And here one practical example for shear stress, like in structural steel members where there is fabrication works. You can see that two plates or two, suppose these are the purlins of a roof truss. These two has to be connected by a bolt. Suppose in industry we'll get only 12-meter plate, but the length of the member is the 16 meter. So they have to lap it. They will lap it through this way and connect it through the bolt. Because of the forces acting on that purlin or the member here, on this screw, at this spot where there is a uh, overlap of both the members, this will undergo the forces in this direction. Since these forces are parallel to this cross section, we call these forces as shear stresses. I hope this is clear regarding the shear stress. And we got 5 more minutes. I will conclude the shear stress here. Shear stress is internal resisting force acting, remember, parallel by the area parallel to the cross section what we are talking about. And coming to the units and the symbol, you remember here, it's a Greek letter tau. Shear stress is denoted by tau, and the units are same as normal stress. Why? Because it is also a stress, it is also stress, the units will be same. Again, the same story will repeat, unit conversion, etc., etc. And I have a given example here for the shear stress. Let's end this session by this example, and we can meet tomorrow. A square bar, it means whose cross section is in square shape, is subjected to the axial load along the axis. That's why it's called axial load, 10 kilonewtons. Find the shear stress on the plane XX, on the plane YY in Newton per meter square. Take the square cross-sectional area as 10 square meter. It is a good question with a simple logic, which I have mentioned here. You have to apply that. They asked me only, remember that only shear stress they have asked me. So I will find only shear stress. Don't waste your time finding the normal stress. Coming to the finding the shear stress, I want to know what is going internally, so I'll, yeah, anything to say? Okay, I cut this member at this section and I will study only this member, and this way of studying the member by cutting is called free body diagram. You just cut the member wherever you want and apply all the external as well as internal forces developed, then apply the equilibrium. If I cut it here, internal resisting force is equals to P. But my aim is to find the shear stress. Shear stress is resisting force parallel to the cross section by area parallel to the cross section. But here, the resisting force parallel to cross section is 0. There is no resisting force acting here to maintain this equilibrium. So 0 by 10. Hence, shear stress at this section is 0. You have to remember this because there is no need of any resisting force acting in this direction to maintain equilibrium. If my applied load is like this, then the shear stress will be not equal to 0. It's some other value as per the magnitude of the load. Clear? I hope it is clear. After the class, you can reverse through this PDF till the date. So the first question is over. Shear stress acting on the plane XS is completed. Now coming to the shear stress acting on the plane YY. Nothing is no question is difficult. You just break the question into simpler parts and solve it and merge the final answer. That is the end of the story. So shear stress acting along YY. This is the section here, and is again apply the formula internal resisting force parallel to the cross section by area parallel to the cross section. So if the external load is P, to resist this load, internally P has to act, equilibrium maintained, end of the story. But for this plane, this P gets the components. Here it is P cos 45, P sin 45. You understood that? To maintain equilibrium, for this plane, this P splits into two components here. You remember that? Next, my formula is internal resisting force parallel to cross section. So which force is parallel to cross section? Either this or this. Comparing to these two, this is parallel to this cross section. This is perpendicular to this cross section. So I have to use P sin 45 by area parallel to the cross section. In the question, I have given you area vertical in the vertical plane, but my area has to be this. So don't make the mistake by taking the 10. It is its component along this direction. So again, I will go back to the basics of trigonometry in our 11th, 12th classes. So what I'm saying is the simple definition here is the area to be taken should be the area of the cross section where we want the shear stress. So here the cross section is not this one, but the cross section is this one, this incline. But in the question, the area was given for this type of cross section, which is 10 square meter. But area of this is not known. But what they have given is angle made by this plane with the vertical. So using the data, how to extract that area is, our desired cross section is this. The given data is this. So by trigonometry, sin 45 is up in a triangle. If I given triangle, sin 45 is, if I take it as OAB, sin 45 is OB, opposite side by hypotenuse OA. So obviously OB is equals to AO into sin 45. But we want AO here. So AO is equals to OB by sin 45. That is root 2 OB. And our OB area is 10 times root 2. I will repeat it again. We want shear stress on this plane, but we have area of this plane, but we also have the angle made by this here. This forms a triangle. As per the properties of triangle, sin 45 is equal to the opposite side by hypotenuse. It's not only side, we can apply the same by opposite area by hypotenuse area. Then we get, by sending it to there, OB will be equal to A naught sine 45. And but still, since we want this, I will make it as subject. AO is equals to OB. If I go it there, sine, it becomes in denominator. So sine 45 is 1 by root 2. So OB by 1 by root 2 is root 2 OB. But OB, this area cross section is 10 square meter, so it is 10 into root 2. That's why I'm using here area as AXS, that is 10 and into root 2. After feeding this data, we will get it as 5 into 10 power 6 for the shear stress along the inclined plane. So we got the answer. Except for the second part also, this is also completed. I guess you understood this. You are able to hear me, right?
Yes.
Yes, sir.
Yeah.
Yes, sir.
Apologies from my end. I think hearing there is a voice issue. From next session, I will try to make it perfect. So
Okay, thank
it's
you.
the end. Yeah, it's the end of the session. I will summarize that. I've just given you example about how to use the handbook and how to do some conversions through some examples. And I have explained it about the stress basically, and then the type of stresses, normal stress and shear stress. This is the pace. From tomorrow, we will slightly increase the pace to cover this topic in upcoming 6 days. Okay. So if any reviews, any doubts, please let me know.
So first of all, thank you so much for this vast explanation on concept. It was quite good. Thank you so much.